Stellar galaxies differ significantly from ordinary galaxies, primarily because of the extraordinary rate of star formation. In these galaxies, new stars are born extremely quickly, often orders of magnitude faster than in ordinary galaxies such as our Milky Way. This intense burst of star formation can result in the formation of several hundred stars per year, compared to about 1 or 2 stars per year in the Milky Way. Star formation bursts can be caused by a variety of factors, including interactions, mergers with other galaxies, or even internal dynamics within the galaxy itself. This frenzied star formation activity has a profound effect on the physical and visual characteristics of stellar galaxies. Large numbers of young, hot stars light up these galaxies, making them incredibly bright and luminous in certain wavelength ranges such as infrared, ultraviolet, and radio. In addition, the increased activity generates significant amounts of dust and gas, resulting in dynamic and often chaotic regions where new stars and star clusters are born. Energetic processes within stellar galaxies also lead to powerful winds and supernova explosions that can drive gas and dust out of the galaxy, affecting subsequent star formation and potentially extinguishing the starburst over time. In addition, starburst galaxies provide key insights into processes in the early universe and galactic evolution. Conditions within stellar galaxies are thought to resemble those in the early universe, when galaxies form stars at a much faster rate. By studying these celestial forces, astronomers can better understand the complex interactions and triggers that lead to star formation and galaxy evolution over billions of years. Flaring galaxies are thus both exceptional laboratories for studying extreme astrophysical processes and crucial elements in building a broader picture of cosmic evolution. Ring galaxies are a rare and fascinating type of galaxy characterized by a distinctive ring-shaped structure surrounding a central nucleus. Unlike the more common spiral or elliptical galaxies, ring galaxies exhibit a prominent circular band of stars, gas, and other celestial material. This striking shape is usually formed by energetic and dynamic processes, most often resulting from galactic collisions or close encounters with other galaxies. One of the primary mechanisms for the formation of ring galaxies is known as a bullseye collision. In this scenario, a smaller intruder galaxy passes right through the center of a larger galaxy. The collision creates a density wave that propagates outward from the collision, compressing the gas and causing intense star formation along the way. This results in a ring of bright, newly formed stars forming around the nucleus of a large galaxy. The gravitational interaction of such a collision can also disrupt the structure of the original galaxy, resulting in a distinct ring pattern. Ring galaxies, due to their unusual formation processes, provide a unique window for understanding the dynamics of galaxy interactions and star formation. By studying ring galaxies, astronomers can gain valuable insights into the behavior of gas and stars under the influence of gravitational perturbations. These galaxies also serve as natural laboratories for studying the effects of galactic collisions, including angular momentum redistribution and triggers for new star formation. With these observations, ring galaxies not only mesmerize with their aesthetic beauty, but also deepen our understanding of the complex and dynamic nature of the universe. A galactic halo is a vast spherical region that extends far beyond the visible boundaries of the galaxy, enveloping the galactic disk, where most of the stars and other luminous matter resides. This halo consists of both luminous matter, such as old stars and globular clusters, and significant amounts of dark matter, which neither emits nor absorbs light but exerts a gravitational influence. The halo extends several times beyond the radius of the host galaxy, creating a rare but intriguing frontier for astronomers. One of the most interesting mysteries of galactic halos is the nature and distribution of dark matter within them. Observations of galaxy rotation curves, where stars in the outer regions of galaxies rotate faster than can be explained by visible matter alone, point to the presence of vast amounts of dark matter in the halo. This elusive substance makes up about 85% of the total mass of the universe, but its exact nature remains unknown. Understanding how dark matter is distributed in galactic halos may provide important clues to unraveling the mystery of dark matter, which is one of the most serious problems in modern astrophysics. In addition, galactic halos are home to some of the oldest and most metal-poor stars, representing the fossil record of the early universe. Studying these ancient stars can provide insights into the formation and evolution of galaxies, as well as the conditions the universe was in shortly after the Big Bang. The halo also contains streams of stars that are remnants of smaller galaxies that have been absorbed by a larger host galaxy through merger. These stellar streams provide a glimpse into the dynamic history and growth of galaxies over cosmic time. In addition, interactions between the dark matter of the halo and the visible components of the galaxy may help us understand the fundamental processes that determine the formation and stability of galaxies. Galaxy mergers are transformational events that play a crucial role in shaping the structure and evolution of galaxies. When galaxies collide and merge, their massive gravitational forces interact, leading to significant changes in their individual characteristics and the formation of a new, often more massive galaxy in the process. These collisions can cause bursts of star formation, black hole activity, and redistribution of gas and stellar matter, thereby having a profound effect on the evolutionary trajectories of the respective galaxies. One of the most dramatic effects of galaxy mergers is intense star formation, known as a starburst. As galaxies merge, their gas clouds collide and contract, creating regions of high density that favor the birth of new stars. This burst of star formation can produce hundreds or even thousands of new stars per year, far exceeding the typical rate of star formation in most galaxies. These newly formed stars, as well as remnants of the original galaxies, contribute to the formation of a more massive and often more irregular galaxy shape, sometimes resulting in elliptical galaxies. In addition, galaxy mergers can lead to the activation of supermassive black holes at the centers of colliding galaxies. As the merger proceeds, gas and other matter rushes into the central regions, feeding black holes and igniting quasars, or active galactic nuclei, AGNs. These unusually bright and energetic events can significantly affect the environment, heating the gas, dampening further star formation, and sometimes ejecting material from the galaxy. The redistribution of angular momentum and gas during mergers can also lead to the formation of various structural features such as tidal tails, bridges, and shells, which are observable remnants of these cosmic collisions. Over long periods, repeated mergers and interactions contribute to the overall growth and evolution of galaxies, changing their shape and stellar population. Through these complex processes, galaxy mergers are key events that define the dynamic and ever-changing nature of galaxies, offering valuable insights into the broader cosmic evolutionary history. Ultra-diffuse galaxies, UDGs, are a fascinating and enigmatic class of galaxies characterized by their large spatial extent and low surface brightness. Despite their size, which may be comparable to that of the Milky Way, VDGs contain only a fraction of the number of stars found in typical galaxies of similar size. The scattering of star clusters makes them appear ghostly and dim, and they are often difficult to see in conventional telescopes. These galaxies provide fascinating insights into galaxy formation and the role of dark matter in the universe. VDGs are important in several key areas of astrophysical research. First, Their existence challenges traditional models of galaxy formation. How such large but sparsely populated galaxies form is still an open question. Some theories suggest that UDGs are failed galaxies that have lost much of the gas and dust needed for star formation through various processes such as supernova feedback, tidal disruption in galaxy clusters, or early cosmic events that heated and expelled their gas. Other theories suggest that VDGs formed in a dark matter halo that is less efficient at star formation than their more luminous counterparts. The composition and dynamics of VDGs also provide critical data for the study of dark matter. Given their low stellar mass, VDGs are dominated by dark matter, providing a favorable environment for studying the behavior and distribution of dark matter without the complex baryonic matter interactions seen in more typical galaxies. Studying the motion of stars inside VDGs can provide valuable clues about the nature of dark matter and its role in galaxy formation. The discovery of galaxies such as Dragonfly 44, which appears to be 99% dark matter, emphasizes that these galaxies have the potential to make breakthroughs in our understanding of this elusive component of the universe. In addition, VDGs enrich our understanding of the diversity and complexity of galactic populations. Their unusual characteristics are forcing a rethinking of galaxy classification and evolution, pushing the boundaries of our knowledge of the cosmos. As more and more ODGs are discovered and studied, they will continue to shed light on the dynamical processes that govern galaxy formation and the fundamental properties of dark matter, deepening our understanding of the complex tapestry of the universe. The local group of galaxies, which contains our Milky Way, is relatively modest in size compared to some of the colossal clusters found in the universe. The local group consists of more than 50 identified galaxies and is about 10 million light-years in diameter. They are dominated by three large spiral galaxies: the Milky Way, the Andromeda Galaxy, and the Triangle Galaxy, with many smaller satellite galaxies orbiting around these giants. In contrast, massive clusters such as the Virgo cluster, which is part of the even larger Virgo supercluster, contain thousands of galaxies packed into a comparable volume. Gravitational interactions in these large clusters are much more complex and stronger due to the higher density of galaxies. Structurally, the local group can be described as loose. The galaxies here are bound together by mutual gravitational attraction, but they are relatively separated, allowing vast cosmic distances between members of the group. This contrasts with closer clusters, where galaxies are in close proximity to each other and often interact through collisions and mergers, resulting in dynamic and often spectacular cosmological events. Interestingly, the quiet nature of the local cluster provides a more stable environment for studying individual galaxies and their evolutionary processes, not subject to the more chaotic dynamics seen in large galaxy clusters. The Virgo supercluster, also known as the local supercluster, is a vast cluster of galaxies and groups that spans about 110 million light-years. It includes more than 100 smaller groups and galaxy clusters, including our own local group. This supercluster plays a key role in the grand structure of the cosmos, being a major node in the tangled cosmic web, where galaxies and clusters are connected by huge threads of dark matter and gas. Its gravitational influence plays a crucial role in shaping the large-scale structure of the universe, dictating the motion of galaxies within its boundaries, essentially acting as a local gravitational attractor in the cosmic landscape. Within the Virgo supercluster is the eponymous Virgo cluster, a particularly dense region containing more than 2,000 galaxies. This cluster acts as a dynamic center, contributing significantly to the overall gravitational pull of the supercluster. As galaxies rotate and migrate within the supercluster, They undergo interactions and mergers that promote star formation and galactic evolution. The Virgo supercluster is part of an even larger structure known as the Laniakea supercluster, which contains about 100,000 galaxies and illustrates the hierarchical nature of the universe. Understanding the Virgo supercluster and its place in the cosmos helps scientists piece together the large-scale distribution of matter in the universe, revealing the underlying structure driven by both visible and dark matter. Cosmic voids are vast, empty regions of space that can be tens to hundreds of millions of light-years in diameter. These voids are one of the most striking features of the large-scale structure of the universe and play an important role in the distribution of galaxies. Surrounded by denser regions of galaxy clusters and superclusters, cosmic voids create a kind of cosmic forest that defines the boundaries of these dense structures. Because the voids contain a much lower density of matter, they exert a lower gravitational pull than their surrounding regions, causing galaxies to migrate to denser regions over time. The existence of these voids affects how galaxies clump together, giving rise to the complex filamentary webs we see in the universe today. When matter flows out of the voids into denser regions, it enhances the gravitational collapse of these regions, resulting in an even greater concentration of galaxies at the edges of the voids. This complex dance results in the characteristic structure of the cosmic web, and the voids represent empty spaces within this web. Researchers study these voids not only to understand the distribution of galaxies, but also to investigate the properties of dark energy and dark matter, as the behavior of voids can provide critical insights into these mysterious components of the universe. The multiverse theory proposes the existence of an infinite number of universes beyond our own, each with its own laws of physics, constants, and conditions. This idea is based on several advanced concepts in theoretical physics, including inflationary theory, string theory, and interpretations of quantum mechanics. According to inflationary theory, proposed by physicist Alan Guth, the rapid expansion of space-time immediately after the Big Bang may have created multiple bubble universes, each expanding and evolving independently of each other. String theory, with its many potential solutions to the fundamental structure of the universe, offers a landscape of possible universes with different physical parameters. In addition, the many worlds interpretation of quantum mechanics implies that every possible outcome of a quantum event gives rise to a new, parallel universe. Although the multiverse theory remains largely speculative, some circumstantial evidence supports an active debate among physicists. For example, the fine-tuning of constants in our universe, such as gravitational force or electron charge, seems incredibly specific to the formation of life. This has led some to argue that a multiverse could explain why the parameters of our universe fell within this narrow range that allows for the existence of life. Of the countless other universes, at least one of them was bound to have the right conditions. Another intriguing, albeit indirect piece of evidence comes from the cosmic microwave background radiation, CMB, the afterglow of the Big Bang. Anomalies and cold spots in the CMB can be tentatively interpreted as fingerprints of other universes interacting with our own. However, these interpretations remain highly controversial and are not universally accepted in the scientific community. The multiverse theory, exciting and expansive, awaits more empirical evidence and theoretical breakthroughs to move from speculation to mainstream acceptance. Wormholes, also known as Einstein-Rosen bridges, are hypothetical tunnels connecting different points in space-time, potentially allowing instantaneous travel between distant regions of the universe. These fascinating constructs derive from the equations of the general theory of relativity, Albert Einstein's revolutionary theory describing the structure of space and time. In 1935, Einstein and his colleague Nathan Rosen explored the concept of bridges connecting two separate points in space-time, which led to the idea of wormholes. The theoretical foundation is based on the notion that the curvature of space-time, under the influence of mass and energy, can create shortcuts through the four-dimensional continuum in which we live. Two main types of wormholes are often discussed in the scientific literature: passable and impassable. Passable wormholes theoretically allow matter to travel from one wormhole mouth to another without physical obstruction or destruction. However, for a wormhole to be stable and passable, it would require exotic matter with negative energy density to keep it open, which has yet to be discovered or understood within the current scientific system. On the other hand, impassable wormholes, such as those described in Schwarzschild's solution to the general theory of relativity, collapse too quickly to pass through, making them impractical for travel. The speculative nature of wormholes has not diminished their appeal in both scientific discourse and the popular imagination. If passable wormholes existed and were found or created, they would revolutionize our understanding of space travel, potentially allowing travel over vast cosmic distances far greater than the speed of light, as well as allowing time travel under certain conditions. Although there is currently no empirical evidence for the existence of wormholes, they remain an exciting and provocative consequence of the mathematics underlying the general theory of relativity, and inspire ongoing research into the fundamental fabric of our universe. The holographic principle is a revolutionary concept in theoretical physics, according to which all information contained in any volume of space can be represented as a hologram, a description encoded at the boundary of that space. This principle emerged from research into the nature of black holes and the difficult problem of black hole entropy. In the 1970s, physicist Jacob Bekenstein proposed that the entropy of a black hole, which is a measure of its information content, is proportional to the area of its event horizon, the boundary beyond which nothing can escape, rather than to the volume contained within. This idea was further developed after Stephen Hawking's discovery that black holes emit radiation, now known as Hawking radiation, which causes black holes to evaporate and poses an information paradox for the black hole. How can information about matter absorbed by a black hole be preserved? The holographic principle, put forward by physicists such as Gerard Tufte and Leonard Susskind, provides a potential resolution to this paradox. It implies that all information about the three-dimensional interior of a black hole is encoded on its two-dimensional event horizon, much like a hologram. This idea has been extended to a broader cosmological context using the ADAS-CFT correspondence proposed by Juan Maldacena in 1997. Within this principle, a theory with gravity in a higher dimensional space, anti-de Sitter space, can be described by a lower dimensional quantum field theory, conformal field theory, without gravity, which is at the boundary of that space. The holographic principle has profound implications for our understanding of the nature of the universe, suggesting that our tangible three-dimensional reality may be a projection of data stored at the cosmic boundary. This theoretical idea offers new ways to address fundamental questions about quantum mechanics, gravity, and information. Although still speculative and an area of active research, the holographic principle continues to inspire new approaches to understanding the deepest layers of physical reality and the ultimate fate of information in the universe. Theories of brain cosmology suggest that our observable universe is a three-dimensional brain embedded in a higher dimensional space, often referred to as volume space. These ideas are an extension of string theory, which posits that fundamental particles are one-dimensional strings rather than zero-dimensional points. Within this framework, the concept of a brain, short for membrane, naturally emerges, with different types of brains ranging from zero-dimensional points to higher-dimensional structures. The most compelling aspect of brain cosmology is that it offers an intriguing new perspective on the fundamental nature of our universe, potentially explaining some of the most puzzling mysteries of modern cosmology, such as the hierarchy problem and the nature of dark matter and dark energy. One widely discussed model within brain cosmology is the Randall-Sundrum model, proposed by physicists Lisa Randall and Raman Sundrum in 1999. This model suggests that our universe is a three-dimensional brain embedded in a five-dimensional volumetric space. What makes this concept interesting is how it can solve the hierarchy problem, which raises the question of why gravity is so much weaker than other fundamental forces. Within the Randall-Sundrum framework, gravity can propagate into additional dimensions of three-dimensional space, making it appear weaker in our three-dimensional brains. Another implication of brain cosmology is the possible interaction between our brains and other parallel brains, potentially leading to observable cosmological phenomena such as cosmic strings or brain collisions, which may even be responsible for events such as the Big Bang. These theories also offer new ways to conceptualize dark matter and dark energy. Dark matter could be particles that do not interact with the electromagnetic forces of our brains, but are felt gravitationally because they exist in neighboring parallel brains. Dark energy could be an effect of higher dimensional geometry affecting our brains. By extending our understanding of the universe beyond the familiar three spatial dimensions, brain cosmology provides a richer tapestry for solving the mysteries of cosmology and particle physics, offering new avenues for experimental confirmation and discovery. Axions are hypothetical particles proposed as a solution to a problem in quantum chromodynamics, QCD, a theory describing strong interactions in atomic nuclei. Introduced in the late 1970s by Roberto Pecci and Helen Quinn, axions arise through a mechanism that solves the so-called strong CP problem. This problem is due to an unexpected symmetry in QCD, which theoretically should allow larger charge parity violations, CP, than observed, especially in processes involving neutrons. Axions help suppress these disturbances, providing an elegant solution to the discrepancy. Intriguingly, axions are also promising candidates for dark matter, an elusive substance that makes up about 27% of the mass and energy of the universe, but interacts very weakly with ordinary matter and electromagnetic radiation. Because of their extremely low mass and weak interaction with ordinary matter, axions behave more like waves than canonical particles. Unlike more massive dark matter candidates, such as WIMPs, weakly interacting massive particles, axions can form a huge, all-pervasive field that subtly influences gravitational effects on galactic scales, while remaining undetectable by direct searches. Several experimental efforts are underway to detect axions or axion-like particles. One well-known method involves using highly sensitive detectors in strong magnetic fields aimed at converting axions into detectable photons. Experiments such as the Axion Dark Matter Experiment, ADMX, are designed to search for these photon signals. If axions are discovered, they will not only provide a solution to the strong CP problem, but will also solve one of the deepest mysteries of cosmology by revealing the nature of dark matter. In this way, they will bridge the gap between particle physics and astronomy, offering a unified view of the forces shaping our universe. The concept of cosmic inflation provides a compelling explanation for some of the most puzzling aspects of the early universe. Inflation, proposed by physicist Alan Guth in 1980, suggests that a fraction of a second after the Big Bang, namely from about 10 circles of -36 to 10 circles of -32 seconds, the universe underwent a period of extremely rapid exponential expansion. During this short epoch, the universe has expanded at least 10 times in circumference, 26, effectively smoothing out all the irregularities and bringing the cosmos into a state of extraordinary homogeneity. One of the main mysteries that inflation solves is the horizon problem. According to standard Big Bang cosmology, different regions of the universe have no way to communicate with each other due to the finite speed of light. However, the background cosmic microwave radiation, the CMB, exhibits nearly uniform temperatures over vast distances. Inflation explains this uniformity by assuming that prior to the inflationary phase, the entire universe was small enough for thermal equilibrium to be established.